Let's take a look at this second reaction mechanism example, where we're asked to determine the overall reaction, our reaction mechanism, identify intermediates, and draw our potential energy diagram. So our first step is to determine our overall reaction. We can do this by combining our reactions together. So what I'm going to do is I'm just going to look to see if there's anything that's on both sides, to see if there's anything that cancels out. And right away, I'm able to come up with my overall reaction. Now I know that anything that was canceled out is a reaction intermediate. So therefore, if I wanted to look at my intermediates, there are 4 of them. Okay. And then if we want to determine our rate law is equal to K times the concentration of my reactant raised to some power. So now I'm going to look to see how many times does this reactant appear before my slowest step. And so it's not in the slowest step. It's not in a step before the slowest step, but it's in the step 2 before the slowest step. And it has a number 2 there. So therefore, this would tell me M is equal to 2. So my rate law would be equal to K times NO2Cl with the second order. Okay. Now, the final thing we're asked to do is we're asked to draw the potential energy diagram for this reaction. So, and we're told that our overall reaction is endothermic. Okay, and so before I add my mechanism, what I'll do is I'll add my overall reaction. Since I know that it's a endothermic reaction, I'm going to start off with my reactants down here. Just double check what the reactant is. Okay, and we know that since it's endothermic, my products for my overall reaction will be up here. And we know that we have to join them. Now we can label a couple of things on here. The difference between my starting point and my finishing point. This is my enthalpy change for my forward reaction. And this is going to be a value greater than 0 because it's an endothermic reaction. You could likewise label this my delta H for my reverse reaction. So if I went the other way, we know it's going to be less than 0 because a reverse reaction is exothermic. We can label from my starting point to the peak of the potential energy diagram. This would be my activation energy for my forward reaction. And to the peak of my potential energy curve from my starting point, this would be my EA for my reverse reaction. Okay. Now, if we wanted to now add this reaction mechanism to it, there's 3 steps in this mechanism. So since there's 3 steps in this mechanism, that means I'm going to have 3 bumps. And my slow step is my 3rd step. So that tells me that my rate determining step is my 3rd step. And it will have the highest peak. So now what I'm going to have to do is, oh, my graph moved over. What I'm going to have to do is I'm now going to add, to show my reaction mechanism, this is going to be the peak of my 3rd. I could put a peak there for my first, and my second. I'm not given any information, so I don't know. So I'm going to come up for my first. I would come down, come up for my second, come down. So there's my first elementary step. There's my second elementary step. There's my 3rd elementary step. And I arrive at my overall. It doesn't have to be super graceful. But as long as your rate determining step has the highest peak. And then you could come in, and if you wanted, you could label the reaction intermediates that are found in each of the values, right? So in this first reaction, I'm going to have ClO2, I'm going to have N2O, and I'm going to have ClO. And in this one, I'm going to have a reaction intermediate NOCl formed. So I could see where my reaction intermediates are.